Hello. In this video, we're going to continue solving basic trigonometric equations. And as I've mentioned before in other videos, by basic, I mean where the coefficient A is 1, B is 1, C is 0, K is 0. So essentially, you're solving for either sine, cosine, or tangent x equal to a number. All right, so this one, we're going to solve tangent x equals 2.35. So here's the graph. You've got your tangent functions here, right? Of course, you got your asymptotes. And I've already put out your solutions. Here's y equals 2.35. It's a line, a horizontal line straight across here. So essentially, everywhere that there's an intersection with the line and one of the tangent functions, you have a solution. So right here, right here, right here, right here, etc. And the idea is, as you're reading these, how do you read these solutions? This time I've got them in radians. And here's 0, here's 5. So it may be difficult to read, but here's like 1, here's 1, 2, 3, 4, 5. So let me just write that down in here so you can see it. Here's 0, here's 1 radian, 2, 3, 4, and here's the major line 5. So you can see this first is just a little bit past 1 radian. Here you're a little bit past 4 radians, and that's how you'd start reading them, right? On the x-axis, that's the angle in radians. All right, so to solve this though, I'm already showing you the solutions, and they're in different colors. I start in green here, and every other one is green, and then here every other one is red. There's a reason for that. We'll come back to that. So when I solve the basic trigonometric equations, this is what I ask myself. Again, I've gone through this a lot in other videos, so I'm not going to read them out. You can pause the video and read them yourself. And so I'm going to go ahead and start solving. So if I have to solve for the angle x that makes this true, remember I asked myself for what angle is, and actually even before I say is, I always ask myself, where am I allowed to look? So in, and with the tangent, here's what you're allowed to look for in what restrictions right here, right? So I'm allowed to look from negative pi over 2 to pi over 2, but really it's like this, right? Negative pi over 2 to pi over 2 not included. The endpoints are not included because those are asymptotes. So obviously that's not going to work. So for what angle in here in this interval is the trig ratio, right? In this case, since we're talking about tangent, we're looking at y over x, right? So where is this trig ratio equal to 2.35, all right? So really what you're saying, though, is that this slope, right, y over x, is about 2.35. So for every 1 unit horizontally in the x, you've got about 2.35 in the y. So the y is about 2.3 times 5 times as much as the x in terms of movement, right? So again, what you're looking at is something like, well, let's go ahead and find the answer so I can make a better drawing. So first place I'm going to do is I'm going to take the inverse function, right? So I'm going to say here, inverse tangent of the angle x is the inverse tangent of 2.35. Right, so then these cancel each other out because I'm theoretically correct here. Is now the inverse tangent of 2.35, and you're going to put that in your calculator, and then it's going to tell you, well, that's going to be 1.16848 radians, right? Understood, radians. Now, what that means is on my unit circle, I'm sorry, that's not quite nice and line and plumb and all that, but what can I say? So I'm about 1.6, so about one radian will be about 57.3 degrees. So I don't know, something like that maybe. 1.168, radians, right? So there I am, and I rotated that much, and essentially what it's saying is if this is the y movement, right, and this is the x movement, that the the length of this y coordinate is 2.35 times as much as the length in the x coordinate, right? Because that ratio is 2.35. All right. So what it's telling me is this is, the calculator is telling me this solution. But then I've got to ask myself, where else on the unit circle or the circle is it that I also have this ratio? And remember, here, this could be, they could both be positive or they could both be negative, and the ratio comes out positive. So really, if I just go out 180 degrees, or pi, right, and then again drop to the x-axis, what I'd find is the ratio of this y coordinate, or y length, to the x length, right, is 2.35. The only difference is you have both x and y movements being negative, so their ratio ends up being positive. So where is this? Well, essentially that's just pi away, right? So you could say, so there's a couple ways you could solve this, right? For, just so you can see this. So we found this right here, the calculator solution. This is 3a, right? And then let's look at here. Again, I'm being, 3a, 3b and all that. Once you start solving these a lot, you just sort of flow. The other solution we found would be 1.16848 plus pi, right? It's exactly pi away. So that's just your other way of doing this. So if you do that, you're going to get 4.31007, right? So this is the other, what I call the other solution. Okay, so that's 3b. And then when I go to write these, 3c, when I go to write the generators, and again, this is all my terminology, the other solution and generators, but it's just for you to kind of follow along what I'm asking you to, follow me with what I'm finding. So you've got your first solution. Either x is 1.16848. Now here, what I'm assuming is I start here and I go 2 pi around, either in the positive or in the negative direction, which is what we've been doing, right? 2k pi. Or you have x equals this new one, 4.31007 plus 2k pi. So that means you're now starting at this solution and going 2 pi, another 2 pi, or going this direction. But essentially, you're saying that they're two separate solutions and they're not equidistant. The truth is they are equidistant. So in this case, we really can come up with one generator, since they're really just pi apart. That's what we see. If I start here, I'm only pi away from this solution. Then when I'm in this solution, I'm only pi away from that solution, and so on and so forth. So actually, I can combine these and just say x equals 1.16848 plus k pi. Again, k is an integer. The difference is, between these, is that here I was using a 2, right? And here I'm just using understood a 1. That's the big difference between them. So let me just show you how this works out. If I do what I was doing with the sine and cosine, where oftentimes the solutions are not equidistant, then I'd start with each generator, right, or each solution, and then just add 2k pi. So I would get these values when I start putting in integer values in for k. But that's basically what I'm saying here is, if I look at this one, so let me just pull this up a little. If I look at the 1.16848, which is right here, well, then I go 2 pi. So if I go forward, bink, bink, let's see, I'm now here at this one. So I started at 1.6848. Now I'm at 7.45167. So that was adding 2 pi. If I started here and I go back 2 pi, then I go to 5.11471. And I go back another 2 pi, negative 11.39789. If I start here at 4.31, that's this one. Again, I could hop and go 2 pi, get to 10.59326. Or I could go backwards, right, and get to negative 1.97312 and go backwards 2 pi, 8.25630. But instead, if I combine them, like I was saying to you, that because they're equidistant, I can just use 1 pi instead of 2k pi, because that's the actual distance between them, right? When you look at the picture, the distance between them is pi. Then what I could do is have one generator, and watch what happens. Let's see if I can, where's the other generators? Here we go. So I don't know how much I can fit in here, but here's what you're seeing. When I use the one combo generator, here at k equal -6, I'm at this -17.68108. Then at -5, I'm going to be at the -14.539. When I'm at -4, I'm at -11.3979. When I'm at -3, I'm at this one, 8.25630. So what you're seeing is you're going, bink, 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 bink. You're capturing them all. It's just that you're going to have to go more, put other values in your K, because your actual generator is slightly different, and it's capturing them all. So what's happening then is you start, let's say here, and you go pi, add pi, add pi, add pi, or subtract pi, subtract pi, subtract pi, subtract pi, and so on and so forth. So that's why you can capture them all at once with one generator. All right? All right, and then of course if you want specific values, right, within an interval, you just figure out what ones fit in your interval, okay? All right, thanks so much for listening. And let me just go ahead and do this, give you a moment to pause that. You might want to take a picture if you want to compare. And then let me also show you this. And you can pause that and compare. Thanks so much for listening.